My name is Dennis Burrell. I'm the Senior Product Manager for Ventev, covering antennas. And today we're going to take a look inside Wi-Fi 6E and aesthetics. So when we're talking about Wi-Fi 6E and aesthetics in particular, we're talking about challenges in network and wireless deployments. For Wi-Fi 6E, the challenges are automated frequency coordination not being finalized by the FCC. What this means for a company like Ventev, which is a third-party antenna supplier, is no external antenna use. That's big for us because we pride ourselves on our antennas and our designs. So therefore, this is something that we need to continually look out for and see where the FCC is going. From that perspective, we've come up with some designs that I'll just go over a little more. Also, as far as for aesthetics, there's a demand for what I call inconspicuous Wi-Fi, and that's a rise in demand. Most mounting and deployment options for Wi-Fi equipment is not as desirable as it was in the past. We see that a lot of vendors now, a lot of our customers are looking to hide their Wi-Fi. They no longer want to see it on the ceiling. So they want to come up with innovative ways to hide the Wi-Fi. They want Wi-Fi, but they don't want to see it. So let's talk about some of our Wi-Fi 6E solutions, and specifically our small form factor line of antennas. The diagram or the picture to the right shows the footprint progression of our antennas, starting with our original patch antenna, which was about approximately 9 by 9 inches. And since then, we've gone through what we call our small form factor design, where now our latest design, which is our femto patch antenna, is 3.4 by 3.4 inches. We've approximately decreased the size by 3 times. And these are all 6 dBi antennas, by the way, just to give you an idea or a baseline to where these designs started from and how we've progressed to making them smaller. Now, you can see that the Pico Patch 2 antenna, which is the dashed outline footprint, is smaller than the femto patch. Well, the Pico Patch 2 is a 5 gig only design, so that's why it's smaller. But the femto patch is the smallest 4-port dual band antenna that's out on the market. So what we wanted to do was we wanted to take this antenna and make it a 6E, so tri-banded to include the 6E frequency band. Now, we know that we're still waiting for the FCC to come out with their AFC timeframe and when that's going to be available. But we wanted to go ahead and start doing designs where we've somewhat future-proof. So if we have these already deployed, when Wi-Fi 6E comes out, we already have antennas either in the marketplace or that's been deployed where you only have to swap out the access point. So here's some of the specs on the femto patch antenna. And to the right, that's the actual picture of the antenna deployment. Pretty sleek, pretty smooth, rounded edges. The gain, like I said earlier, 6 dBi. The VISWAR with the voltage standard wave ratio is 2:1. That VISWAR just tells you how much power is transmitted versus what's reflected back into the radio. A VISWAR of 2 is around 90% of the power is being transmitted, only 10% being reflected. And that's across the frequency range of operation for the tri-band. The half power beam width is 80, 120, and 120 for 2, 4, 5, and 6 gigahertz respectively. And then the vertical beam width is 80, 50, 50, 2, 4, 5, and 6 gigahertz respectively. And then the front to back ratio, 9 dB, 15, and 15. Now, there are a lot of antennas out there, or directional antennas, where that front to back ratio is larger or higher. But in this design, with the trade-offs that we did to make it a smaller size, we were still able to achieve acceptable front to back ratios for this antenna. And once again, the dimensions 3.4, 3.4, and it's only 1.4 inches thick. So this isn't a very big antenna dimensionally.
So am I correct in saying that the 6 dBi gain is uniform? Am I understanding that correctly?
That is correct. So a little bit more about that. The 6 dBi gain. The 6 dBi gain. When we spec out antenna as far as the gain, we spec it at the connector. So this takes into the cable loss. One of the things that we do in our numerical analysis when we're going through the design of our antennas is we want to take all of that into account. Now, one of the things about 6E, for the cables that are currently in place and out there, they're only rated up to 6 gigahertz. So what we had to do based on the cables that we use when we're going into production of these antennas is that we had to characterize these over that 6 to 7 gigahertz frequency range and what the losses are. And then based on those losses, we took those into account when we went in to do the design of the antenna and to optimize the performance. Also, this antenna design specifically utilizes FR4 material. So for that material, we had to characterize it as well across that 6 to 7 gigahertz frequency range and take those losses into account when we were designing the radiating structure as well as the feed network.
So there's not any meaningful insertion loss or anything strange that we would run into that's not accounted for already there.
That is correct. All of that, we take that into account when we go in. So in our numerical analysis in which we use HFSS, all of those are put into our simulator when we go through the simulation. And then we simulate to get the best gain, insertion loss, return loss, and also port-to-port isolation. And we use those parameters to fine-tune the antenna. So I kind of mentioned some of the things that we do as far as for the simulation. So let's just go over some of the patterns just to give you guys some ideas of simulated versus measured performance of the antenna. To the left are the patterns, both simulated and measured for 2.4 and 5 gigahertz. Pretty consistent if you look at the two patterns, top and bottom of the 2.4 and 5 gigahertz band. To the left are the simulated for the E and H plane. And then to the right of those four are the measured. The beam widths and the patterns pretty much look the same. But once you start doing testing, anechoic chamber testing, you start to see the interaction of the cables as far as radiation and current on the cables. So that's where you get the shaping on the back side of the antenna with the lobes and the front to back ratio. So you can see the difference between the two, where you see more interaction on the cables and you're seeing the side lobes or the lobes on the back side of the antenna. Now, like I said, for the simulated performance for the antenna on the 6 to 7 gig, what we had to take into account, like I said, was the cables and all of those types of things, the cables and also the connectors, because the connectors are only rated up to 6 gig as well. So the shift from going to your standard 2.4 and 5, moving into Wi-Fi 6E, and then even higher based on the typical or standard cables that's used in Wi-Fi, that characterization of those components need to take place by the cable manufacturers and the connector manufacturers. As far as us trying to get ahead of everything and plan accordingly to future-proof for some of our designs, we had to characterize those in-house on our own and then use that in our simulation and in our design criteria. If you look at the patterns between the 6 and 7, both simulated and measured, the beam width characteristics and capabilities still look the same, but you can see some differences in the patterns, specifically on the vertical or the elevation patterns. You're seeing somewhat of this distortion, but we still are able to achieve the beam widths and the beam widths for both the 6 and the 7 gigahertz. So we're pretty proud of what we were able to achieve in such a small form factor. Now, this isn't the only designs that we currently have. I just wanted to highlight this. We've taken some of our highest runners as far as our antennas, and we've started designing or redesigning them to cover the 6 gigahertz band. Pretty much going through the same type of criteria and tested methodologies, but just want to make sure that we have antennas readily available when AFC is ratified and approved, so that we already have antennas ready to go. Let's talk about some of our aesthetic solutions. A lot of you guys may be familiar with our raised floor tile antennas. We came up with this patented solution about 6 years ago. And what we did was we took a concrete raised floor tile and we embedded one of our planar antennas into this floor tile. So typically in the Wi-Fi deployment, you have what we call a top-down or ceiling to floor type of design with the antennas either on the access point or external antennas. This gives you a bottom to top approach, very stealthy, very inconspicuous design for floor to ceiling. The antenna is designed to hit so that it reaches the client device in a maximum height for the client device. The patterns are designed such that it achieves maximum performance at the average or typical client device height of 3 to 3.5 feet. The picture to the left shows the actual tile that's been deployed in an office environment with the carpet pulled back to show what it looks like. The center picture actually shows the access point connected to the floor tile. The access point either sits on the floor or sits in a carrier or some type of mount that we have also that connects to the pedestal. And then the picture on the right just shows once the carpet is over it, you don't even know that it's there. So these are the different types of solutions that we have. And I'll just briefly go over each of them and then I'll concentrate on a couple of them just to give you an idea of some of the things that we're doing. The Global IFS tile was our original manufacturer that we worked with. They're the leading raised floor tile manufacturer in the US. We had an exclusive agreement with them for 5 years. We did some pretty well-known, established designs that's out in the marketplace using these floor tile antennas. While we had this exclusive agreement with us, some of the other top flooring manufacturers reached out wanting to do some work or do some business with us, but we couldn't do anything with them because of that agreement. But once that agreement was up, we wanted to expand our footprint in this area with raised floor tiles. So we started working with the other top manufacturers of floor tiles in the US, that being ASM and Tate. The Global IFS and the ASM floor tiles are similar in the sense that the antenna is embedded into the concrete floor tile. Embedded into the floor tile. The Global IFS solution is a concrete floor tile, whereas the ASM solution is an aluminum floor tile. So let's just take a look quickly at some of the characteristics of the Global IFS floor tile, and then we'll move into the Tate, which is a different design and what I want to highlight as far as what we're doing with the Tate. As you can see, what I wanted to highlight on this is just the loading, the concentrated load for this specific floor tile is 1,500 pounds. We also have a solution that's a 1250 that is 1,250 pounds. The thing that I wanted to highlight is that these are the exact same characteristics of the standard floor tile without the antenna embedded into it. So we were able to achieve the same loading characteristics with the antenna embedded compared to the standard floor tile, which is something that we definitely highlighted to anyone that was looking at using this. Another thing about these floor tiles that I would like to mention is that having this ability to do this type of design gets us further back into the decision-making process. So now we're at where we're meeting with architects that's going through new building design, looking at raised access flooring. We're actually having conversation with the architects now because they're deciding on the floor. And now when we go to meet with them, or the manufacturers of these floors go to meet with them, they bring up that they have a Wi-Fi option for these and start bringing up the aesthetics play. So this gets us back earlier into the decision-making process as far as for wireless. And then the antenna specifications, 3 to 6 dBi antenna. And to the left, down at the bottom, you can see the radiation characteristics of this antenna, of this floor tile antenna. Another thing that I would like to mention about these antennas, these floor tile antennas, is that we also currently have a solution that is Wi-Fi 6E capable. So we have a solution that covers 6 to 7 gigahertz, you know, from the perspective of wanting to future-proof a design if a customer is wanting to put this in or install this into their buildings.
So Dennis, I see that your gain here, you're expecting a 2.4 is around 3 dBi. Is that, does that include sort of a loss due to cross polarization you're expecting, or is that not something y'all see often? Or are we looking more at sort of neutral at, you know, carry level? How does that shake out?
Right. So so this gain is specific to a chamber measurement. As far as the cross polarization, what we're seeing when we go and actually do testing of these in situ and in the building is that we're seeing that with the multipath, we're not seeing a big drop off from this 3 dBi gain on the 2.4. And in fact, these antennas are closer to the client device compared to them being mounted on the ceiling. So we optimized it for that. So we're pretty confident in that gain that we're meeting, that we're seeing at both of those frequency values.
Okay, yeah, it's not too exaggerated, so I wouldn't think it'd be too far off, especially being so close. But
right. And then the other thing, I mean, that's a great question. And then the other thing that we had to take into account as well is the types of flooring that's going to be going over, that's going to be covering these tiles, because they don't ever put in bare tiles. So we're talking carpet or we're talking vinyl. The original design was optimized for carpet. So we see a slightly, a slight difference between a carpeted performance as opposed to putting vinyl laminate over it. As long as that, and we've actually done some deployments where they put a wood over the floor as well. The only caveat to these designs or to these deployments as far as the flooring material is that any of the materials where they have a magnetic backing will not work with these floor tiles.
could you deploy something like this inside of a Faraday shielded facility? So like if they have it in the exterior walls, is that going to cause you any issues, like say with conduction near the edges of the facility, or just a non-issue?
Well, not inside the facility, but as far as penetrating, no, on the outside. But you may see some degradation on the edges of where the Faraday, where you have an interaction between the two.
Interesting. It's an interesting use case because you know you can't put it in the ceiling like that.
Right.
Thanks, Dennis.
So, quick question.
Hello, DoD.
Under these are all listed as being 4-lead models. Do you have a 6-lead in-floor tile antenna?
Yeah. Yes, we have a 6-lead version, and like I mentioned earlier, that actual 6-lead version is Wi-Fi 6E capable. We was working with a customer that had this awesome building design, and we actually got a chance to work with them and use some of their simulation tools to actually do fine-tune our design at the coverage coverage frequency of 6 to 7 gigahertz. So yes, and we currently are fine tuning or finalizing 8-lead design as well. So let's talk about the Tate floor tile. So this is what I wanted to bring up that I wanted to highlight. I didn't mention the ASM because it has similar characteristics to the global IFS design, but it's an aluminum floor tile instead of concrete. The Tate is a concrete floor tile, but they weren't looking for the antenna to be embedded in the concrete. They wanted to come up with a slightly different solution. I'm sure pretty much to differentiate themselves as far as having a wireless solution for their floor tiles compared to the other manufacturers. So what we did with Tate is we worked with them to embed our junction box antenna. A lot of you guys may be familiar with that. That's one of our innovative designs as well, where we've taken an antenna and we've designed it into both a 3-gang and a 4-gang junction box. So imagine your light switch on the wall. That's the junction box, and we've come up with a novel way to integrate an antenna into that. So we've taken that antenna and we've worked with the electrical box manufacturer to come up with a design where instead of the normal electrical box that goes into these floor tiles, if they have a Wi-Fi solution, they take that same box that has an antenna integrated into it and use that for their Wi-Fi. To the left shows the different product variants that we have. Both 4-lead, a 6-lead, and we're currently working on an 8-lead junction box. And once we get that ready for sale and production, then we're going to transition that into a solution for Tate as well. So this right here shows propagation and what we call an omnidirectional versus directional propagation. So we have 2 types of electrical boxes. One has the junction box embedded into it that shoots our RFL signal straight up, which we call our omnidirectional version, providing max coverage. And then we have what we call a directional. We have the junction box, but it's actually attached to the side of the electrical box, and it's more for a directional type of coverage. Long hallways, that type of thing, utilizing this solution. Now, also, the one thing I like to mention about these, the junction box antenna, is that it does have some articulation. So by moving the arm, you can adjust the articulation of the antenna to get more directionality in that scenario. Right here, this just shows the completed box, what the box will look like that we get from the company that we work with called Accor when they integrate our antenna into the box. You see the cables coming out the side, the circle out the side of the box, and then the cables. So the antenna cables, like I said, you can either have the access point on the floor, or we have a carrier type of mount that the access point fits on that attaches to the pedestals that hold up the floor tile. Now there is about no more. You have to have at least 5 inches of clearance to utilize this type of solution. And the other thing that I would like to mention for this is the concentrated load is 2,000 pounds for this box as well. This box sits flush to the top of the floor tile, and it has a sleeve in it where you can put a piece of carpet or whatever the covering material that they're using in the deployment. And this just shows the characteristics of the antenna. Now, this antenna that we have here, this is a directional, but we also have an omnidirectional junction box antenna as well. So we have 2 different types of designs that's suitable for these types of access flooring deployments.
Get these in just I mean, do you have to buy like the whole tile system, or can you get just the mounts and then you can do your own tile cutting and get them installed that way?
Yes, great question, Scott. So what we provide or what we sell is we sell the electrical box as the solution. So if this is going to be deployed by the flooring manufacturer, or this could actually go in any other flooring manufacturers that use these electrical boxes. What we sell is we just actually sell the finished solution of the box with our antenna integrated in it. So you could theoretically just buy that and do your own cutout in your floor and utilize these.
Cool, thank you.
Go ahead, man.
And is there enough room in that box to have the AP and the antenna?
No, the AP goes under the floor. So it's just the antenna inside the box. The AP fits up under the raised floor.
Ever given any thought to having a box that can contain both? So that someone could use this as a solution for a floor where they know that, you know, they want to keep access to the antenna, the AP, or change the antenna or whatever, but it's a tiled floor. So they would be pretty much like your solution for ceilings, for ceiling tiles.
Right. A great question. We've looked into it a little, but we haven't gone in depth into it. We came out with this solution and like your question that has come up. So we're investigating it as well.
Why not like even move it maybe a little bit on the side or something like that? So AP, you can just use an AP bracket and just mount it that way. Can you move that a little bit on the, on one side further?
We can do that. We can do that. And also, just to the point that she just made, we have a design or solution where the actual antenna is on the side of the box as well. So we probably could seat that antenna or seat that access point in the lower portion of the box and just angle based on the articulation of that antenna on the side to provide the coverage.
If I wanted like a 30 or 40 degree beam width, could you guys get that out in short order?
30 to 40 degree beam width, that would call for a large box. Because with 30 to 40 degrees, you're talking about an antenna with a gain upwards of above 8 to 9 dBi.
Yep. So I have an application where if I could have, like a 30 degree beam width and actually have an inline attenuator, that would be ideal because I have a fairly unique environment I can't quite go into, but.
Okay. We could definitely look into something like that for you.
Okay.
Like Jared mentioned earlier, if it's a problem, we like to try to solve it. All right. Now, the last thing that I want to discuss, one of the designs that we're really proud of that we just started deploying and doing some proof of concepts with is what we call our R-friendly floor tile. So this is actually a floor tile that we designed to use with APs with internal antennas that you want coverage, but you don't want to see the AP. So the AP sits up under the floor tile. Now, we're using the global IFS concrete floor tile, the global IF manufacturer for the first designs of this floor tile. And what it has is it has 9 3 by 3 inch windows cut out in the steel on the bottom of the floor tile. So pretty much you have these RF windows or these RF friendly windows under the bottom of the floor tile. And then the access point sits in that area where the windows are cut out. And then this also has an adjustable tray. So if you look at the diagrams or the drawings, the top view is your concrete floor. The bottom view is the steel with the windows cut out. So the white portions would be concrete. And then the side view just shows the concrete, the steel plates, and the windows as well. So then, like I said, we have an adjustable tray as well. Oh, one thing that I like to mention about those windows, the reason why we came up with the 3 inch by 3 inch windows is that we wanted to be able to transmit through the concrete at 2.4 gigahertz, and the wavelength at 2.4 gigahertz is less than 3 inches. So that's why the cutout of 3 inches, 3 by 3 inches for the window cutouts. Now, that being said, as long as we take into account what the wavelength at 2.4 is, we're fine at 5 and 6 to 7 gigahertz because those wavelengths are smaller. Now, the bottom view to the left shows the steel plate, then the window with the cutout, and then the AP in the bracket. The picture to the right shows the bracket that we have, which attaches to the 4 pedestals of that hold up the floor tile, and that tray is adjustable, so you can raise it, lower it to optimize the performance. What we found in some of our testing that we've been doing, and we've been working with a couple of companies that's testing this solution, is that there's an area depending on the AP that's used that is optimized based on this distance from the bottom of the concrete floor tile or the window that's cut into the floor tile. And then you see the side view, which shows the concrete, the steel plate, and the window as well with the AP and the bracket. We're very excited about this option. We've gotten some good feedback. We're testing it now. It's actually available for deployment, and it's a patented design. So we've submitted for a patent for it. The patent is pending.
If you're doing a deployment that's leveraging, this would be huge if your deployment is leveraging BLE radios that are built into the access point, because those are usually not supported in the external antenna. Has any of your testing revolved around how that may work as well, and what BLE arrays are looking like coming through the windows provided? And
we have not done any testing with our customers on using BLE. More so was just some coverage to see what the coverage looks like under the concrete tile and the actual heat map and radiation through the tile.